Alright, let's spend some time on the electrophilic addition of HX. This is a hydrogen halide across a double bond, an alkene. A couple things that we need to be aware of whenever we do electrophilic additions across an alkene. First is regiochemistry. That's going to be the orientation of the addition of HX. We'll see that it's going to be important for other systems as well. And we should always keep in mind stereochemistry. That's not always every single case we have to be aware of stereochemistry, but we should keep it in mind in case our reaction is stereospecific. For example, what we previously saw with E1 versus E2. E2 was very stereospecific, so we just need to bear in mind that's something we always have to think about when we look at these reactions. So the first one, let's just take something like this. This is 1, 2, 3, 4. This is a 2-butene. It's a 2-methyl 2-butene. Okay, and we're reacting it with hydrobromic acid. When we do that, there's only one product we observe, and that is we only observe where the hydrogen is on this carbon and the bromine is on that carbon. The product that's not observed is having the hydrogen on this carbon and the bromine on that one. Now, obviously, I can add my HBr in either orientation. It can go this way, or it can go this way. So the question is, why is this orientation not observed and only this one observed? And that is what we mean by regiochemistry, the orientation of the addition. Okay, so let's take a look at our mechanism. So if we look at our mechanism, the first step for an electrophilic addition is the addition of the electrophile. So step 1 is that I take my 2-methyl butene and I add my electrophile. And there are two ways I can add it. If I add it for the first product, I would be adding my H plus here and forming my carbocation at this carbon. The other place I can add it would be here, and I'd form my carbocation right here. Well, as you can see, this one is a tertiary carbocation, and this one is a secondary carbocation. And as we've discussed previously, secondary carbocations are not as stable as tertiary, which is why you only get this observed product. So when we take this carbocation this is actually what is available from my nucleophile. To attack. And that gives us our final product. Okay, so less stable, more stable. So this is what's formed. Okay, that leads us to Markovnikov's rule. Okay, so, and I'll give you an extended aspect of Markovnikov's rule. So there's two ways we can talk about it. So, Markovnikov's rule goes like this. Markovnikov. Okay, and that is the proton acid adds to the carbon to the double bond. Okay, in a product. See, adds to the double bond, results in a product where the hydrogen is on the carbon with the most hydrogen. Okay, so in this case, it's adding on to the carbon that has the most hydrogens. This had none, that had one. So that's where the hydrogen goes to. But in a more general sense, when we think about Markovnikov's rule, so more generally, okay, the electrophile adds to the alkene. Okay, let's put this back up here. Generally, the electrophile adds to the alkene to form the most stable intermediate.
Yeah.
And you see that's going to be the case in a lot of different electrophilic addition reactions that we see. So let me go through and give you a couple examples. All right, so predict the major product if I have 2-methyl propene hydrochloric acid. Okay, and suppose I take 1,3 how about, let's see, buta 1,3-diene plus HBr. Now you can propose the products for that too. Okay, so 1 mole here, 1 mole there. So let's do problem 1 first. Okay, so 2-methylpropene. So here's 1, 2, 3. That's propene. And 1, 2. Here's my methyl group. I'm going to add HCl. Okay, so remember to form a most stable intermediate, or the more specific sense where the hydrogen goes on the carbon that has the most hydrogens, I put the hydrogen here, I put the chlorine there. So what you would get is something like that. Okay, now what about 2? Okay, 2 butyl 1,3-diene. So 1, 2, 3, 4, 1,3-diene, 1, 2, 3, 4. I'm going to add HBr. Now what's interesting here is I can add HBr across here. This has more hydrogens than this one, so you get something like CH3, Br here, and I can get CH3 and Br there. Now how is this possible? Okay, so let's take a look at my intermediate. So suppose I add in my electrophile there. Okay, so here is my carbocation intermediate. But remember, this has an allylic carbocation intermediate. Which means I can actually have resonance. And when I have resonance, move the double bond here, I'd have this. This is a plus charge. Now my bromide can attack there. And that's how I can get this product. Okay? Now between these two, which is my major product, well, don't forget, this is an alkene that has 1, 2 substituents. This alkene only has 1. So it turns out that this one, interior, is my major product. Okay? So let's stop here and we'll move on to doing an antimer compound.